All right, here's a tougher one. So this deals with a frozen pond and a sled sliding along it. So we've got, let's see, frozen pond, and we've got a sled. And the sled, it's a 13-kilogram sled. It's given a kick that imparts to it an initial speed of 3.7 meters per second. So basically, someone pushes this a little bit, kicks it, gives it some energy with that interaction, and it has an initial velocity right after the kick, V naught, of 3.7 meters per second. The coefficient of friction between the sled and the ice, so the coefficient of kinetic friction, because we've got sliding going on here, is 0.11. No units, because coefficients of friction do not actually have units. Find the distance the sled moves before coming to rest. In other words, how far it goes until it comes to, well, rest means it comes to a stop. The acceleration of gravity is 9.8 meters per second squared, okay? So, let's look at this from the energy viewpoint, because we've been looking at things recently from the energy viewpoint, which is good, because that's the section we're in. I have some kinetic energy at the beginning, and something happens because I lose all of that kinetic energy. We're on level ground, so we don't have a change in our potential energy due to gravity, nor do we have any springs in this, so we're not actually looking at any potential energies. The energy that we're dealing with for our object is basically the kinetic energy, and it starts off with some, which we're going to find here in a minute, and then it ends with none, which means something had to remove that energy. What brings the sled to a stop? Well, whenever you have stuff sliding, it's going to be friction. That's why we're given information about friction. That's also a clue in case you had any trouble on that, but that's okay. They want to know the distance the sled moves before coming to a rest. Okay. Well, we're trying to find out about energy being taken away from something. So, how do we transfer energy? We can either put energy in or we can take it out, and we call transferring of energy, at least right now, work. We know work energy theorem. And that's going to be my final energy minus my initial energy. We can find the work done by friction. Well, the work done by friction, well, let's start off by finding our change in energy, actually. We'll come back to the work done by friction, because if I start filling in too many equations, I know that can get a little bit difficult to follow. So, the only type of energy we're dealing with is, we know that the work done is going to be equal to our kinetic energy, because that's the only type of energy we have in this problem. My final kinetic energy minus my initial kinetic energy. All right, well, my work is then going to be equal to 1/2 mv squared. We said that the mass is 13 kilograms times v final for my final, but v final was 0 meters per second, quantity squared, because at the end, the sled comes to a stop. So 0. Minus 1/2 13 kilograms times my initial velocity, which was 3.7, if I recall correctly, meters per second, and we're going to square that because that's our equation for kinetic energy. So this is 0 minus, well, look at that, our work is going to be negative 3.7 squared times 13 times 1/2. I come up, if I've done this correctly, with my work being equal to negative 88.9, actually 89.0. 89.0 joules. Kilogram times meters squared per second squared. This is also joules, that's 0, so we had 0 minus that, and it's just negative 89 joules. That's the work done. So friction has done this much work, it has taken this much energy out of our system, bringing that sled to a stop. All it had was 89 joules to begin with in kinetic energy, and friction has now taken all of that away. And here's where we start using our next equation. Work is also the force times the displacement times cosine of the angle between them. Well, hey, the displacement is actually what we're looking for, how far the thing goes. Now, it's going to the right, and which way is our force? The sled is moving to the right the way that I've drawn it, but the force of friction is actually going to oppose that. My force of friction is going to be to the left. So if my force is to the left and my displacement is to the right, we're going to end up with 180 degrees between them. So here we go. We're going to say that this is the force of kinetic friction times my displacement times cosine of 180 degrees, because my displacement is to the right and my force is to the left. Now, the problem is we need to replace the force of friction with something, but it's the coefficient of kinetic friction, which we have, awesome, times the normal force, which we don't have. Now, I've been playing kind of fast and loose on this. Technically, it'd be good to draw a free body diagram. That's how I can tell which way my force of friction is. Force of kinetic friction is this way. We're going to have a normal force up, holding the sled up, keeping it from falling, and we have the force of gravity down, which is going to be equal to mg. If I do my sum of forces in the y direction, like we learned back in forces, we'll find that my normal force is actually going to be equal to mg. I can now plug that in. My coefficient of friction is 0.11 times my normal force, which is going to be the mass, 13 kilograms, times g, which is 9.8 meters per second squared, times delta x, which I don't know, times cosine of 180 degrees. And here's the last part. My work, we found above, is equal to negative 89.0 joules. 0.11 times 13 kilograms times 9.81 meters per second squared times delta x times, if you plug in cosine of 180, you'll find that it's negative 1. I want to solve for delta x, so I'm going to divide by all of these things. I'm going to take 89 divided by 0.19 divided by 13 kilograms divided by 9.81 divided by negative 1, which is what's going to get rid of my negative. And I'm going to take this number divided by 0.11 divided by 13 and divided by 9.81. And that's going to leave me with just delta x over here, and of course divided by negative 1 as well. If I've done this correctly, we come up with, I didn't use 89, I just had what was in my calculator here, but that's fine. We get something like 6.34 meters. You might get something a little bit less or a little bit more depending on rounding error. The actual answer that we have for this problem is 6.34972 meters. This should be accepted as a correct answer. This one's a little bit more complicated. It brings in that we're using both forms of work energy. So we're finding the work done by looking at our change in energy. That was the transfer of energy. And then after we find our work, we find that it's negative because we've removed energy. We then set that equal to the work done by the force of friction. Here's where that cosine of the angle between them comes into play. The force of friction is to the left, but we're moving to the right. That means we have cosine of 180. That means that this is actually doing negative work. It's taking energy out of the system. Those negatives will end up canceling out for us, and that's why we get a positive delta x, because that tells us that we have moved to the right in our displacement. If we got a negative, it would have told us that we moved to the left instead. Again, all of these signs will work out if you use them